This is the one I'm talking about. Okay, so let's look at this bowling shuffle. So Steve, are you okay so far?
Yeah.
Okay, let's look at this bowling shuffle problem. Okay. So this bowling shuffle problem is that convinced that happy cow get the more milk. Farmer John had installed a giant disco ball in his barn and planned to teach his cow to dance. Okay, whatever this is garbage. Looking at popular cow ball dance, Farmer John decided to teach the cow how to do bowling shuffle. Bowling shuffle consists of his cow 1 to 10,000, 100,000, okay, N, okay, they are N cow, okay, at least N number can be 1 to 100,000, okay. Line up in the same order is a successful shuffling, each of which potentially reorder the cow. So it will reorder the cow, okay, it will potentially reorder the cow. To make it easy for his cow to locate themselves, Farmer James mark the location of his cow with position 1 to N. Okay, so it's 1 to N. So first cow in location 1 and next 2 and then up to N. A shuffle with A1 to AN move one position I to AI in the shuffling. Okay, so every cow moved to the new location during the shuffle. Unfortunately, all AI are not necessarily distinct. So multiple cows may move to the same location during the shuffling, after which they move together for the remaining shuffling. Conventional notice that some position lineup contain cows in them, no matter how many shuffle take place. Please help him count out the number of the such positions. So you have first line input of n, that's the number of cow. Okay, so you have 4 cow. And then here you contain integer a1 to an. So you basically you have so this problem when you have a1 to an, you can convert it to array format. So it's a0 to a n minus 1, okay? This one we don't discuss. So this is 3, 2, 1, 3. You can change it back to 2, 1, 0, 1, okay? That's easier. So now you have 0, 1, 2, 3. This one 0 shuffle to 0 shuffle to what? 0 shuffle to 3. I'm sorry. Let me redraw it. So 0 shuffle to 3, 1 shuffle to 2, 2 shuffle to 1, and then 4 shuffle to 3. Okay. Okay, now this one is a shuffling network, okay? Now the question is that please output a number that always has contained cow, no matter how many shuffle take place. So how to solve this problem? Right here you have 0 go to 3. This actually 1 go to 2, 2 go to 1, 3 go to 3. So if you get started from 0, this location 0 will disappear, right? This location 0 will disappear. So then you become 1, 2, 3. So 1 will go to 2, 2 will go to 1, 3 will go to 3. There's no longer 0, right? And then 1 will go to 2, 2 will go to 1, and 3 will go to 3. So 1, 2, 3 will remain, and eventually you will have 3 of them. So this one, how can we, based on this input network, to analyze eventually how many of them will be staying, no matter how many shuffle take place? Because they might be, let's assume that we may have 0, 1, 2, 3, 4, 5, 6, 7. Okay, let's assume that this we don't go to 0, 1, 2, 3, 4, 5, 6, 7. So 0 go to 2, 2 go to 1, 1 go to 2, 3 go to 4, 4 go to 3, 5 go to 6, 6 go to 7, 7 go to 7. Okay, let's assume this is the one new one. So what will happen is 0 will disappear. 5 disappear. Okay, so the array that no one go to will disappear for sure, right? For sure, right? And then how can you know that a number go to some location and it will always be there? How can you know that this number will always be there? Okay, there's a question. How can you prove that a number is always be there? Or can you pick something that you will disappear? Okay. One way to do it is that no matter what network you set up, you just keep running for a certain time and making sure that you just check it, which one it exists. But that would take, say, you have order of n and you need to run order of n times, so you will end up with n square algorithm to solve this problem. Or for sure, you should be able to solve the problem using the n square algorithm. But I think that's not the solution. Okay, that's not what you want to do. That actually would take a longer time to figure out. Okay. So one way is that if you some number that you don't have someone going to, okay, then those are out. Those are out. Okay, so 0 go to no one go to 0. No matter 0 go to where, 0 go to 0, that actually is dead. Okay, 0 go to nowhere, then 0 is dead. So what I can see is that actually you do reverse array, and then you see there's a 1, 2, 3, 4, someone going to, the number that someone going to, as long as you are someone going to, then the number, I think it will stay. As long as you show up in the number right here, I think the number would, every stage that will stay. Let's check this hypothesis to see if that's true. So we have 0, 1, 2, 3. We have 0, 1, 2, 3. Let's assume that we actually go 0 to 1, 2 to 1, 1 to 2, 3 to 2. This one no one go to, we delete them. This one no one go to, we delete them. You will go to 1 and 2. 1 and 2, 1 will go to 2, 2 will go to 1. That actually is okay. So this 2 will stay. So then you delete the number that no one go to, then the remaining one, your state always has someone that go to. Should be fine, right? So if we delete this one, the zero since no is not going to going, this zero is dead. So where zero go to actually is of no use. This one may be cut. Okay, let's see. So the state that someone go to, as long as you have this listing, and the state that you have someone go to should, I think it will always be existing because there are always someone who will go to here. Okay, so the state that no one will go to, it doesn't exist, so you can kick them out. Okay, and then those state that no one go to, then the link that they have should not be. You do the second time. You do the second time, so you have one and two left, and the second time the value still exists. I think that's good enough to determine that this is shuffle should stay or not. Okay, so I think only two paths should be enough. Because the first pass, you make sure that you only go to some valid one. Okay, and second pass, if it still be valid, okay, still have some value in there, we can be pretty sure that it should be okay. Okay, so you need to know about which one that has someone coming and which one don't have someone coming. Okay. So you have 4, 3, 2, 1. Okay, let's get started for this one, okay? This one, let's call it borrowing. Oh, no, no, we cannot code it in this way. Sorry. Because it's user code format. We have to follow the user code format, okay? It's called shuffle, okay? So the program that's called is shuffle, and then it's a shuffle.in and shuffle.out, okay? So let me copy a user code problem, okay? Let me copy from somewhere to get the user code problem. Okay, let me copy this one. Okay, this one is called shuffle. Okay, that's delete everything here. Okay, so you need to have this. That's okay. So read in the N. Okay, then let's delete everything else. Okay, and right here we do use a type define. Okay, vector of the integer and vi. Okay, we need a vi type. Okay, and we have a vi type when we read in in. Okay, vi. Okay, and then we do actually we do the next line. So we do for integer. We do while loop. Okay, let's see. Let's actually do while loop. We will do in a number of the data. So do for integer I equal 0, I less than n, I increase. Okay. Then we will do vi the push back a number. Okay. So this number we push back would be from in to you would have a number called integer x read into x, and then we'll push back the x to the array. Okay. Oh, I'm sorry. This bi should be here. It should declare as bi, and here we will do a array. Okay, shuffling array. So we call vi a. So this one should be a the pushback x. Okay. So we push back different x into there. Okay, that's printing. Okay, that's actually write a print vector. So void print vector via. Okay. Okay, so we basically try to enter all the vector and then just print the vector once. Okay. Okay. Then print out the shuffle network. Then I need to have that shuffle the in. It should have 4 and then 3, 2, 1, 3. Okay. Save. Let's go to shuffle the CPP. Let's run it. Okay, so this one print out the shuffling network. Okay. Now next one, we are going to do analysis on this shuffling network. Okay, one thing is for sure is that if on a certain run, your data don't have data go to, then it will not have the number should not let me actually check in this one. So later I can, okay. So let's try to get this one. Bowling shuffle. Use code. Let's go to there. Okay. So I can actually do a submission. Okay. So if there's a no, nobody go to, I think it will definitely uh, have not going to have be useful. Okay. So here, let's see. We don't want to use a super big array what because it's a huge array. Okay. Okay, let's try to use map then. Okay. Let's try to use map. A multiple entry is allowed. Multiple entry is allowed. So let's try to use a set. Okay, so I'm assuming that actually if there's someone going to, then there will be a value. Okay. So I'm counting the number of the distinct numbers. So let's see. This one we push back it. Is stored into the array. So here, if I don't use an array list, let me use a set of I. Okay, so let's see. If I create let's create a set of integer si. Okay, and then let's do si dot insert x. Let's do cout si size. Okay, let me just use si dot size. Okay, so this one, let's do F out. Okay, so the shuffle will get a 3. Let's see. I don't know. Let me submit, okay? See what happened, okay? I just do the shuffling to see how many data is in used. But let me directly uh, return it. Okay, so basically it's wrong, several of them wrong. So you cannot just count the size of the shuffling that's wrong, okay? Basically that's too simple. Oh, look, okay, let's slightly change our algorithm, okay? We previously we look at the we look at the test date, okay? We remove the test date. So just removing the test date is not enough. We should also remove if there's a stay, it only come from the test date and nothing else. Then this one should also be this stay should also be taken away, and that one cannot repeat. Okay, so for example, that everyone go to 2 and 3. And this one only coming from 0, that's also need to be taken away. Okay, so we need to modify our algorithm slightly differently. So in order to do that, we will to look at the count in each state after the counting. Okay, we will look at the count in each state after counting. So here we say we have the x is a new state. I forget to -1 because we have 0, 1, 2, 3. We starting from 0, we not starting from 1. Okay, so we will create another VI. We should create another VI. Okay, here we have VI of the shuffling array. We should have another one called VI after. So VI after, let's create it right here after here. Okay, so here we have VI after, and it's size of n because we have n numbers. And then we have this one a pushback of the xi. So okay, so we should increase the number of the dependency for the dependency that actually. So this after is counting the number of a certain location's count. So when we enter a x, then the people the count that go to x will increase as well. Okay, and a remaining using the shuffling locations. Here we use x -1. Okay, we use x -1. We have to use number consistent with the count order because we have used the -1. So let's do this. Let's use S decrease. I'm sorry, let's actually enter it and then do X decrease and then push in X and then increase the X location. Let's do this. Okay, let's do this. So this A is recording the shuffling network. After of the X is counting the occurrence of each location, a number of cow in each location. Okay, so we do have the number of cow in each location. So our ANS is the answer we want, is the state that remaining for the number of cows. So initially we will have a number of n, okay. So now we need to figure out what are the no cow states. We need to figure out what states has no cow. So let's create a VI no cow. Okay. Then let's go through everything that actually, let's go to for integer I equal 0, I less than n, I increase. Okay, let's go through every single one. Okay, so if the after of the I actually equal to 0, then this one has no cow. So this one has no cow. We will actually do no cows. So ANS keep track of the total number of the state that still have cow. And then we pick out all of the cow that actually the location that has no cow. Now we want to actually remove all of the state that depend on the no cow one as well. So let's see. While so where no cow is not empty, we would try to actually get the last one. Get the last element. Okay, that is the last state that has no cow. And whoever depend on this state, we should also who we actually remain on this one, we should also remove them. So we do no cow. we remove the last element, okay? But we already get it, and we will remove that one. And then we will see who would be depending on this state. So how can I know that who is depending on this state? So if the so-called after or this state decrease, it will equal 0. So actually, it's only the only guy who this one actually is the only guy who actually is depending on the current state. It actually only one element, then that guy need to be removed. Okay, it depending on the test state. Depending on this test state, this state is a test state. And then if there's a certain one that depending on this test state only, then the test state would be removed. So we should actually do no call. What's wrong it, okay? Okay, so we modify in this way that first we calculate the call to recording the shuffling network using the A array. And then this after would be the reverse array, would be counting the number of incoming state. So how many will come to this location? Okay, so here we have 0 go to 3, and then 1 go to 2, 2 go to 1, and 3 go to 3. Okay, so here we do have 1, 2, 3. So this one we actually say 1, 2, 3. We change it to call 0, call 1, call 2. Okay. So our state 0. So let's see. Let's redo it again. We have 0, 1, 2, 3 equal to 0, 1, 2, 3. It says 3, 1, 2, 3. So this one 3 go to we change it to 2. So this one 0, 1, 2. Okay, we minus 1 because the n is 1 to n. So we change it to 0 to n minus 1. So basically your call 0 will go to 2. 1 will go to 0. 2 will go to 1. And then your 3 will go to 2. So this one is an empty state. Okay, this one is an empty state. So here your counter end up to be 1, 1, 2, 2 coming to here. Okay, so this one is 0, 3 incoming to here. So this one after is counting how many will come to here. Okay. After is counting how many will come to here. Here, 0 will come to here. Okay. Okay, and then we create a queue of no call. So we go into there to see if nobody actually will come to here, will come to here. So nobody is depending on it. We will say this one, currently nobody, after here, nobody will come to here. We say there is no call. So this one no call. We decrease those no call one. And we also check if someone is no call and someone also depending on me to go into there, those state we would also decrease. So by doing this, we will get rid of those. We will get rid of those have no call moving to, and also there may be a state, and it depending on a state that actually the state that actually has no call. Both of those kind of the state we will remove them. Okay, and that's actually submitted. Okay, pass. Okay. Okay, let me know if there is any question. Okay, see you next time. Bye bye.